Hello, my dear students. Welcome back. In our previous class, we have learnt potential is nothing but work done per unit charge in bringing it from infinity to that point. Correct? So we came to know that work done is equal to V into Q. So this work done is stored in the form of potential energy. So potential energy is equal to V into Q. If one electron of the charge, what is the charge of the electron? 1.602 into 10 to the power minus 19 coulomb is accelerated through a potential difference of 1 volt. If it is accelerated through a potential difference of 1 volt, then the work done is, if an electron of charge 1 into 10 to the power minus 19 coulomb is accelerated through a potential difference of 1 volt. Okay, if you want as a difference, I can write it delta V also. Delta V is equal to 1 volt. Then the work done is nothing but 1 volt into this charge. Correct? So therefore, I can write work done is equal to 1.6 into 10 to the power minus 19 joules. I can write this work done as potential energy or else in terms of joules. Or else, see here, work, this one I can write it as 1 electron volt also. Tell me why I can write it as 1 electron volt. 1.6 into 10 to the power minus 19 joules is a 1 electron volt. Because when one electron is accelerated through a potential difference of 1 volt, the work done is this much. That means, see, 1 electron means 1 into 10 to the power minus 19 joules. So 1 into 10 to the power minus 19 into 1, you will get the same answer. So you can write 1.60 into 10 to the power minus 19 joules is equal to 1 electron volt. So one multiple choice question, 1 electron volt is equal to 1.602 into 10 to the power minus 19 joules. Keep this in your mind. So whatever answers you got in your problems, you wrote in terms of joules, you can convert it in terms of electron volt. Suppose you got an answer that is work done is equal to 2 into 10 to the power minus 19 joules. Then can you convert this joules into electron volts and write 1 electron volt means so many joules. Then 2 into 10 to the power minus 19 joules means how many electron volts. How can you convert? Cross multiply. If you do 2 into, what you have to do? 2 into 10 to the power minus 19 divided by 1.602 into 10 to the power minus 19. So the answer what you get is in terms of electron volt. This is how you can convert. Whatever answers you get in terms of joules, divide it by 1.602 into 10 to the power minus 19. The answer what you get is in terms of electron volt. Understood? This is how you can convert from joule. See, 1 electron volt means 1.602 into 10 to the power minus 19 joules. 2 into 10 to the power minus 19 joules means how many electrons? 2 into this one divided by this one. So always what the value you have in terms of joules, divide it by 1.602 into 10 to the power minus 19 joule. You will get the answer in electron volt. Because sometimes in the question, if they give the work done in terms of electron volt, then you can convert it into joules, or you can something question if it is in the little bit twisted manner, then it will be in the electron volt, or you may have to write answer in electron volt. That's all. Okay, so I can say 1 electron volt. Or if the question is asked, define 1 electron volt. How can you define 1 electron volt? 1 electron volt is the energy gained by an electron. It is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. 1 electron volt is energy gained by an electron when it is accelerated through a potential difference of 1 volt. Very, very important definition for 1 mark. So what is 1 electron volt? It is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. Okay. Next, we have learned one derivation, that is to write the expression for the potential energy in the absence of the external electric field. In today's class, what we are going to learn is, you are going to derive the expression for potential energy of the system of charges, potential energy of a system of 2-point charges, placed in an electric field, external electric field. You have to find the expression for the potential energy of the system of 2-point charges placed in an external electric field. So let us consider 2-point charges Q1 and Q2 with the position vectors R1 and R2 with respect to the origin. Let us consider that, or let us assume that the 2-point charges are at infinity, just like earlier. Initially, let there be the external electric field. Due to the external electric field, V of R1 be the potential at the point, at a point with the position vector R1. Initially, we want to place the charge plus Q at the point with respect to position vector R1. Then, because of the electric field present, the potential at the point is V of R1. Okay, I want to place this and place it here. Once again, initially, see here, once again, earlier there was no electric field. Now, because of the electric field, let there be a uniform external electric field. Due to that, V of R1 be the potential developed at the point R1. Okay, V be the potential developed at the point R1 due to the external electric field. So while bringing the point charge Q1 with respect to position vector R1, the work done is equal to, what is the work done? Work done is equal to charge into potential. So charge into potential at that point is V of R1. Correct? Earlier there was no electric field. In this case, there is an external electric field E. Due to the external electric field, the potential developed is V of R1 with the position vector R1. I am bringing a charge Q1 from infinity and placing at a point with the position vector R1. So the work done in bringing this charge from infinity and placing at this point is charge into potential at that point, that is V of R1. Next, one more charge I want to bring and place it at this point, that is Q2. To bring that and place it over here, now not only because of this one potential, earlier external potential. So external potential plus potential due to this charge. So two potentials are there. Why two potential? One is due to the external potential, another one potential due to the charge Q1. So therefore, while bringing this charge, the work done in bringing the charge Q2 from infinity and placing at a point R position vector with respect to the position vector R2 is Q2 into In this place, one external V of R2 plus the potential due to Q1. What is the expression for potential due to Q1? Potential due to Q1 is V1 is equal to 1 by 4 pi epsilon naught Q1 by R1P, correct? Now potential due to Q1 on Q2 is 1 by 4 pi epsilon naught Q1 by R12. Understood what it is? See, little bit twisty it is. Initially there is electric field E. Because of that, potential developed is V of R1. So in this external field, I am going to bring one charge and place it, that is Q1 charge. When I am placing here, it has to oppose this electric field then potential. So the work done to overcome that potential is Q1 into V of R1, what is present over here. And now, because of the charge Q1, the potential developed is V1 is equal to V1 by 4 pi epsilon naught Q1 by R1P. Next, I have to bring the one more charge Q2 from infinity and place it at this point. So for that, the work has to be done against the external electric field plus the external electric field's potential plus the potential field developed due to the charge, this one. So at this point, this is with the position vector R1. Here with the position vector R2, it is V of R2. So V of R2 plus position, because of this one, the potential is here, now that one. So therefore, W2 is equal to Q2 V of R2 plus 1 by 4 pi epsilon naught Q1 by R12. Now tell me, what is the total work done in bringing these two charges? Total work done is W is equal to W1 plus W2. That is, what is the total work done? Q1 V of R1 plus Q2 V of R2 plus 1 by 4 pi epsilon naught Q1 Q2 by R12. This is the expression for work done. This work done is stored in the form of potential energy. So therefore, potential energy is equal to work done is equal to Q1 V of R1 plus Q2 V of R2 plus 1 by 4 pi epsilon naught Q1 Q2 by R12. This is the expression for the potential energy over the system of 2-point charges placed in an external electric field. If there is external field, electric field present, then the expression is this one. Understood? Yes. This is also important for 3 marks. Then the next concept which we are moving for is, you have to find again one expression for potential energy of an electric dipole placed in an electric field. Expression for potential energy of a dipole placed in an external electric field. Potential energy of an electric dipole or a dipole placed in an external electric field, you have to derive the expression. What do you mean by dipole? Dipole is a pair of equal and opposite charges separated by the distance 2a. So let us consider a dipole with the charge q plus q and minus q. So, and the dipole moment P is equal to 2aq. Let us place this dipole in an uniform electric field. So, let us bring a uniform electric field. Okay, uniform electric field is there in this direction. Let us place a dipole. Okay, minus q and plus q. Minus q and plus q inclined at an angle theta. Correct? Because the dipole placed in an electric field will experience a torque tau is equal to P cross E. Am I right? If a dipole is placed in an electric field, it experiences a torque tau is equal to P cross E. Okay, what we have done? We have considered a dipole plus q and minus q placed in an uniform electric field. Let the dipole have the dipole moment P is equal to 2aq. We know that the dipole experiences a torque tau is equal to P cross E. Because of the torque, it aligns at an angle theta. I want to neutralize this torque by giving an external torque. Suppose an external torque is given. To neutralize the torque by rotating the, if this is a plane of paper, by rotating the plane of paper from theta naught to theta 1. I want to neutralize this torque. To neutralize this torque, I have to give external torque. Torque means nothing but a force. What the force exists, you have to give one more force to nullify it. Correct? Equal and opposite force should be given. So, to nullify or neutralize this torque, I am giving, suppose if I give a external torque which is equal to that torque, then how to give? I have to rotate the plane. If suppose this is a plane of paper, I have to rotate this plane of paper from theta naught to theta 1 with an infinitesimal angular speed, very small angular speed, and so that there is no angular acceleration. Angular acceleration is 0. Then the work done is nothing but from where to where? From theta naught to theta 1 I have to rotate. External torque applied with respect to the displacement for the small infinitesimal small displacement d theta. Then the work done is this one. See, work done is nothing but force into displacement. Force is nothing but in terms of torque. Torque is nothing but what? The external force we apply, that one. External torque is tau external into d theta. How much I have to rotate the plane of paper? From the angle theta naught to theta 1. What it is? We have considered a dipole plus q and minus q placed in an uniform electric field E. Because of the electric field, the dipoles align themselves in an angle theta with the torque tau is equal to P cross E. Suppose I want to nullify or neutralize this torque by giving the external torque, then I have to rotate the plane of paper with an angle theta naught to theta 1 with an infinitesimal small angular speed, so that there will be no angular acceleration. Then work done is given by integration from theta naught, from where to where I have to rotate? From theta naught to theta 1, tau external into d theta, because work done is nothing but force into displacement. Substitute. What the external torque we are applying here is nothing but same torque, because I have to neutralize it. So therefore I can write work done is equal to theta naught to theta 1 P cross E into d theta. But P cross E can be written as PE sin theta into d theta. PE is constant, take it outside. PE integration from theta naught to theta 1 sin theta into d theta. Integration of sin theta is minus cos theta. So I can write work done is equal to PE minus cos theta from theta naught to theta 1. Apply the limit. When we apply the limit, what do we get? What do we get? When we apply the limit, work done is equal to PE. Upper limit minus lower limit minus cos theta 1 minus of minus plus cos theta naught. Correct? Cos theta naught. Therefore, work done is equal to PE cos theta naught minus cos theta 1. This is the expression for work done, which is stored in the form of potential energy. So I can say what? U is equal to PE cos theta naught minus cos theta 1. This is the expression for potential energy of a dipole placed in an external electric field. What we have done? We have considered a dipole plus Q and minus Q separated by the distance 2a. Let the dipole moment be P is equal to 2aq. Placed in the external uniform electric field E, it aligns itself due to the torque experienced by an angle theta. Then I can say it aligns itself in an angle. I have to neutralize this torque. So what I have to give? I have to give an external torque. By applying the external torque, I can neutralize this existing torque. How can I neutralize? By rotating the plane of paper from an angle theta naught to theta 1 with an infinitesimal small angular displacement, so that there is no with the infinitesimal small angular speed, so that there is no angular acceleration. Therefore, I can say the work done in neutralizing it is from theta naught to theta 1 is tau external into d theta. But tau external is nothing but what? It is nothing but tau itself, because we have to neutralize by giving equal and opposite torque. Therefore, I can say P cross E into d theta. Theta naught PE sin theta, because P cross E is nothing but PE sin theta. Therefore, I can say theta naught to theta 1 sin theta into d theta. Integration of sin theta is minus cos theta. Apply the limit, upper limit minus lower limit. So W is equal to PE cos theta naught minus cos theta 1. This is the expression for potential energy of an electric dipole placed in an external electric field. The next concept which we are moving for is expression for the electric field on the surface of the charged conductor. Okay, before going to the next concept, we'll do one thing. We'll solve one problem related to this one. That will be easy for you if I go along with that derivation. So we'll write one problem, that is An electric dipole Q is equal to plus or minus 8 nanocoulomb of length 4 centimeter when placed with its axis making an angle of 60 degree with a uniform electric field experiences a torque of 4√3 Newton meter. Calculate the magnitude of electric field and also potential energy of the dipole. What you have to do? An electric dipole charge Q is equal to plus 8 nanocoulomb of length 4 centimeter when placed with its axis making an angle of 60 degree with a uniform electric field experiences a torque 4√3 Newton meter. You have to calculate the magnitude of the electric field and also the potential energy of the dipole. How to calculate the magnitude of the electric field? See, it is a dipole. Charge is given. Okay, Q is equal to 8 nanocoulomb. Length. What is the distance between the two charges? 2A is equal to 4 centimeter. Not A, because they have given length of the dipole means 2A. 2A is equal to 4 centimeter. Making an angle theta is equal to 60 degree. Experiences a torque 4√3 Newton meter. You have to calculate the magnitude of the electric field. What is the expression you can use to solve this? We know that tau is equal to PE sin theta. Use this and calculate E. Then which formula we have to use? You have to calculate what potential energy of the dipole. Which formula you can use to calculate potential energy of the dipole? The previous derivation, what have you got the answer? U is equal to, what is the expression you got? Minus PE cos theta naught minus, PE cos theta naught minus cos theta 1. That expression you have to use and you have to solve this one. Okay? Try to solve. Thank you.